Hello everyone. So today we're going to continue on our discussion on 7.1 iterated integral. So if I remember correctly, we get to talk about how to evaluate iterated integral in the last video where I show you some example, and I also mentioned to you a few things that you have to watch out for, namely number one, try to use parentheses separate each layer of the integration so that way you can focus on each one individually. So it help get rid of some of the careless mistake that students tend to make. Two is pay attention to the order of integration because that tells you how to integrate properly, and also make sure you try to put x equal to or y equal to over the limit so that you know where to put them in. And I know you're probably thinking like, "Oh, I'm not gonna make a mistake like that," but trust me, I heard that enough time and I see enough students making that mistake. That's why I'm trying to point it out to you. So it's up to you what you want to do, but that would be my advice. And then the most key mechanic is that when you integrate over one of the variable, you basically treat all the other variable as constant. So kind of like what we did with partial differentiation. And also the way to progress in your iterated integral is that every time you integrate, you should get rid of one of the integral, one of the differential, and one of the variable completely from your integration, from your problem. So that each time you integrate, you're making progress until eventually you only get a constant as your final answers. So that's how you properly do that. So we have three examples on the last video that kind of illustrate to you how to do that. So what I want to talk to you about today is to try to understand the structure of an iterated integral and the connection between a Riemann integral and an iterated integral. So we call that an an iterated integral. Actually came from a Riemann integral. Remember I mentioned that iterated integral is basically a necessary step to transform a Riemann integral into a numerical value. And that's how we actually use to evaluate Riemann integral, is by rewriting it into an iterated integral. So what's important that changes the way it works? So from a mathematical standpoint, a Riemann integral in general will look something like this. I'm writing out a double Riemann integral. And that, we know, is corresponding to an iterated integral that looks something like this. So there's a connection between them. So right now what we're trying to explore is how an iterated integral, which is the one on the right, how does it correspond to a Riemann integral on the left? And once we understand the connection, we would then be able to start from a Riemann integral and rewrite it into an iterated integral and then allow us to evaluate it into an answer. So meaning right now what we're looking at is how to go from the iterated integral to the Riemann integral and see the connection. And once we understand that, we can then go backward. And when we can go backward, then now, meaning that we would be able to evaluate Riemann integral by writing into iterated integral, then writing into and then evaluate into a number. So let's look at the connection. So by looking at these two expressions and the way it's structured, I automatically noticed the following things. Number one, I noticed that the integrand it's implied that f of xy, in this case, equal to x squared y to the third. So that becomes the function that define the surface that we try to integrate. And of course, in this scenario right here, we can interpret our Riemann integral as well as our iterated integral to calculate some kind of volume under a surface. So that's my integrand. So that's pretty simple. Two, I also noticed the connection between the differentials, which in this case, I can see that dA actually equal to dx dy. And remember, this basically defines what we call an order of integration. So to be fair, this dA can also equal to dy dx if you're using a different order of integration. So a general note is that dA, because the differential, area differential, is actually equal to kind of the length times the width, and the length could be called dx and the width could be called dy, or vice versa, depending on which way you look at how to calculate the area. So there's a choice there. As a matter of fact, for a function that went from R2 to R1, there are two different order of integration that you can use, dx dy or dy dx. So then leave the following thing would be the limits. So how does the limit work? So here's the important part. The limits in an iterated integral are used to describe the regions of integration, which in this example we call that B. So therefore, depending on the way we describe B, it changes the way the limits are, for the most part. So now how does this particular example work? So this example basically defines the following. So here's the interesting thing. Not only that you have to look at the limits, but you also have to look at what do they represent. So in here, the limit is 0 to 3, 0 to 2, from the inside integral to the outside integral. But more importantly is this, which is one of the reasons why I asked you to identify what the limits are, because it's important in understanding how it describes the region of integration. In this particular example, if you look at it, because our order of integration is dx then dy, imply that the two inside limits are for x and two outside limits are for y. So therefore, this now basically helps describe the regions B. How? This is how. It basically implies that regions B is described by the following. You identify starting from the inside integral and work your way out. The inside integral tell me that regions B must get between x equal to 0 and x equal to 3. Therefore, defined by using this double inequality. X between 0 and 3. And then the outside integral indicate that y must be between 0 and 2. And so now I can actually try to draw out what B look like. So here's a very simple picture of B. So x equal to 0 is this line. X equal to 3 is this line. Y equal to 0 is this line. And y equal to 2 is this line. And therefore now I can say that B must be this regions right here. That gap between these four straight lines. Notice that B is what we call a rectangular regions. B in this case is a rectangular region. So what is a rectangular region? Because the following. Because in the iterated integral, all the limits are constants. Therefore implied that this region is defined by intersection of straight lines. And more importantly, those straight lines are parallel to the axis, because you have line that is just simply x equal to and y equal to. So therefore you're basically forming horizontal lines and vertical lines. So therefore we form a rectangular regions. Rectangular regions are extremely important in the sense that rectangular regions are very easy to evaluate the integral of. Okay, and yes, you're probably already thinking like, so does that mean that we have to do something called non-rectangular regions? Because it's kind of odd that I brought up rectangular region if there's no mathematically different between a regions that's not rectangular. And you are correct. Non-rectangular regions are actually much harder to deal with when you come to iterated integral, and we will get into that next. Okay, so we're getting there. So what I want to talk to you about would be what's the advantage of a rectangular region? Well, because of the fact that the rectangular regions are defined by simply strict lines, basically lines that parallel to the axis, it makes it extremely easy to reverse or change the order of integration. So therefore, this is extremely important because this only works for rectangular regions. For rectangular regions, it is very easy to change the order of integration. All you have to do is simply reverse the differential and also reverse the inequality integral symbol. You can change the order of integration simply by doing the following: rearranging the differential and the integral symbols. Symbol. And you don't have to do anything else. You just simply rearrange them, meaning the following. In this case, our double Riemann integral of f of xy dA for this region B, for the function x squared y to the third, can be written as this Riemann, this iterated integral, 0 to 2, 0 to 3, x squared y to the third, dx dy. But I can also simply just flip-flop the differential and the integral and reverse the order of which I integrate. And I will get the same exact result. The reason why is because if I look at the second way to write the integrals in dy dx, it still result in the same exact two inequality that's work out the regions. One of the nice things about rectangular regions. And of course, regardless of which way you do the integral, you get the same result. And you might be thinking, then why do I choose to do one way over the other? Well, we'll explain that in a little bit too. Don't worry. So that's for rectangular region where all the limits are constant. And you can basically read off the limits by forming a set of inequality that would describe the regions of integration. So now let's do something slightly more interesting. So if I'm not mistaken, this is our second example that we did. Let me see. Just want to make sure. Oh, this is it right here. All right, there you go. So now let's look at this example right here. Integral from 0 to 2, x squared to 2x, x squared y dy dx. So first of all, let's try to see if we can understand the following. So number one, I identify that f of xy must equal to x squared y. So that would form some kind of surface in R3. I don't know how the surface look like, but I know that it has to be some kind of surface. Two, I know that the order of integration dA is the area differential is in this case defined to be dy dx. So that established what we call the order of integration. In this case, y first, then x. And now finally, I also can identify the regions of integration based on the limits. So once again, remember how this works. So this is my first integration, which is dy, and then outside integration dx, and therefore indicate that the inside limits are y, and then outside limits are x and x. So therefore tell me that our regions of integration B must be defined by using these two inequality. Y, gap between x squared and 2x, while x gap between 0 and 2. Now notice, because of the fact that y is gap between x squared and 2x, and neither of those are constant, therefore indicate that the y is actually gap between two curves. And if you also probably make a connection between what you have seen in our first video, where I told you that if you have a regions in R2, there are two ways to basically describe these regions. One of them is to use two curves from top to bottom, and then two vertical lines from left to right to box it in. Or a second way is to have two curves from left to right, and then two horizontal lines to box it in the rest of the regions. So notice that the way this particular region is defined is y gap between x squared and 2x, and then x gap between 0 and 2. You can see that that is describing the regions B using method, the first method right here on the left. Okay. These two ways are used to define regions that are non-rectangular. If it's rectangular, it would just have all constant in the inequality. Also important to understand is that when you define it using first way or using second way, depending on the regions, you will get two radically different kind of inequality. The reason why, because of the way the inequality is set up. So if you look at this two way to set up the inequality, notice that when I stack up the inequality for y on the first way has the variable x in it. And as a matter of fact, when you're defining a region using a set of double inequality like this, you have to kind of stack them up from top to bottom, where the top inequality are allowed to use any variable that come after it. And each layer of the double inequality you use would use one less variable until you get to the last one on the bottom, where it has to be gap between two constants. That is how you properly describe a region. Which is the reason why it's nice to have a rectangular regions, because they are all constant. So it doesn't matter which way you stack them, it would fit into this description. But now in this case, this is the proper way to describe it. If I reverse these two inequalities by putting a y on the bottom, the x on top, now it's incorrect. Okay? Because we cannot have the bottom inequality have variables in it. As a matter of fact, the lowest inequality should always have just constant. That's how it works. So now let's see if we can identify these regions B properly. So let's see. So seem to me that this tells me that y have the gap between y equal to x squared and y equal to 2x. And x has the gap between x equal to 0 and x equal to 2. So let's see if we can draw B. Let's do a quick sketch of regions B. So let's see. So we have y equal to x squared. So that's simple. That's just a parabola. Y equal to 2x is actually a straight line. Notice that I have these 2 points of intersection. This one should be easy, 0, 0. This one actually comes out to be 2, 4. And notice that is basically what the other two limits are. This is x equal to 0, basically indicate this first intersection point. And x equal to 2, which basically indicate this second intersection point. So it seems to me that here is B. So that's what B looked like, which is pretty good. And the way this B is described right now is that we have a top curve, a bottom curve, and they have two vertical lines to box in these regions. Now here comes the big question. What if we want to change the order of integration to dx dy? what would happen? So first thing I need to point out is the following, extremely important. In this case, B is a non-rectangular region. As you can see, it's actually a gap between two curves, non-rectangular region. Therefore, indicate that it's not unlike the rectangular region where you can just simply rearrange the limit and the differential and allow us to actually rewrite the order of integration. We cannot do that here, meaning you cannot take this integral it's not the same as this. That is wrong. You cannot do that. The reason why you cannot do that is because if you think about the way this integral works is that you have the outside integral. When you're done, you have to plug in x squared and 2x, and therefore result in your answer having x in it, which is not allowed because you're supposed to get rid of x already. So when you get to the outside integral, there's no x, so we can have just an answer, which is a numerical value. See, this setup would not work. Okay, so how do we actually make it work? Well, it's by redefining regions B using the proper inequality. See, notice that right now I'm defining B using these two inequality. Oh, x squared first, 2x. So that's how we describe this region. So this way of describing the regions corresponding to dy then dx. The reason why corresponding to dy then dx because we first describe what's gap between y between what two curves, and then describe x by describing two vertical lines. Okay? So now what I want to do is basically redefine these regions in reverse order, dx then dy. And in order to do that, I have to have x gap between two curves and y gap between two constants. Okay? Remember, the proper way to describe the region is to stack your double inequality, and the one on top are allowed to use any of the variable underneath it. So each layer would have less variable that you can use because there are less inequality underneath it. And eventually when you get to the bottommost one, it should have no variable but just constant because there's no more inequality underneath the last one. So that's how that works. So meaning, in this case, if I want to describe using x then y, my x double inequality can have y in it. As a matter of fact, if it have y in it, it will make it a curve. If it have no y in it, if it just have constant, it will make it rectangular. Okay? So now the question comes down to how? Well, simple. It requires to kind of rewrite our equation. Our y equal to x squared turn to x equal to radical y. Our y equal to 2x turn to x equal to 1/2 y. And because now I need y value to be my last inequality, therefore indicate I have to box my regions in using two y equal to equation, which they are horizontal line. I can now define the two horizontal line to be these two. Some of you might remember doing something similar with area between curves. And that's precisely how this is relating to it. We are literally trying to find the regions between curves properly. Okay? So now I'm ready to rewrite my integral properly. So my integral will be the following. X would actually gap between, now be careful, you have to make sure you write it correctly, the curve on the left to the curve on the right. The curve on the left would be the straight line, which is 1/2 y. And you can identify that by drawing a horizontal line from left to right. You see that hit the line first, then hit the parabola to radical y. And then y would go between 0 to 4. So therefore indicate that our Riemann integral over b, f of xy dA, yes, almost every double Riemann integral looks just like that, except that we're changing what b is and what f of xy is, and then a would choose between dx dy or dy dx. This would transform into this Riemann integral in the order of dy dx, but it can also transform into this integral, which go from dx dy, and therefore we get between 1/2 y to radical y, and then 0 to 4. So that's the proper way to reverse or change the order of integration, is to first start by describe what the region of integration is by setting up a new set of double inequality. And once you do that, then now the double inequality simply becomes the limits. Okay? Notice that the two order of integration will result in completely different limits. You don't simply just flip-flop them. Okay? It also requires you kind of change some of the value and also change which one is go first and which one goes second. So therefore, there's a lot of things that are going on when you try to change the order of integration. Now then come a very simple question. Why? Why would I do one way over the other? Well, it's all dependent on the integration process, because one of them, one order of integration might be easier to actually go through the integration process than the other one. Like in this case, I can see that if I do dx dy, I actually run into radical y, which might cause an issue when I integrate, because it might make it harder. So I don't know. Now, since I have about 3 minutes, I'm going to actually evaluate this integral right here to show you that this evaluation should give us the same answer as we did it before. Hopefully. Okay, I do remember when I did that on the last video, I actually made a mistake. I forgot the 2 in front of the 2x, and I believe I fixed it and have the right answer. So I guess now is the moment of truth. I'm going to try to see if I can do the integral in the opposite order, and let's hope we get the same answer. Mathematically, it should give us the same answer because the volume that we're looking for is not subject to the way we try to evaluate it. It doesn't matter which way we found it, it should be the same answer. So let's hope that it worked out. So the first thing I'm going to do is just like how I always ask you to do. I'm going to ask you to do this. I'm going to ask you to write this. Okay. Remember, you should definitely do that until you get very comfortable with doing this thing and make less mistake. So I'm going to have the outside integral. The inside integral is dx, so it will become 1/3 x to the third y. Evaluate from x equal to 1/2 y to x equal to radical y dy. So therefore become y equal to 0 to y equal to 4. 1/3 radical y to the third y minus 1/3 1/2 y to the third y dy. So if I'm looking at this correctly, that's y to the 3/2 plus y, so become y to the 3/2 plus 1. So 3/2 plus 1 is 5/2, so I think that's 1/3 y to the 5/2 minus 1/2 to the third is 1/8. 1/8 times 1/3 is 1/24 y to the 4th. Okay, so I'm going to lightly cross this out because I have that underneath. So now I'm going to integrate this. So if I integrate this, I would have 1/3 times 2/7 y to 7/2 minus 1/24 times 1/5 y to the 5th. Evaluate from y equal to 0 to y equal to 4. So this seems to me is 2/21 y to 7/2 minus 1/120 y to the 5th. So therefore, when I plug in 0, this whole thing go away. So I just have to worry about the plug into 4. All right, so let's see. So that seemed to be 2 to the 7, because 4 to the 7 over 2 is 4 to the 1/2, which is 2 to the 7. So 4 to the 7, let's see, 38, 64, 120, 128. So times 2 is 256. So it seems to me is 256 over 21 minus 4 to the 5th, I'm going to actually write out as 4 times 4 times 4 times 4 times 4. So make it easier for me to cancel. So I'm going to cancel that with that. That becomes 30. Now 30 times 4 is 120. I'm going to cancel that to a 2 and cancel that to 15. So I think that's all I can do. So I think this is 15. And 4 times 4 is 16. 16 times 4 is 164. Times 2 is 128. So sim to me, what I have is 256 over 21 minus 128 over 15. So the common denominator, I guess it should be 105. So that would require this to multiply by 3. And this I would have to multiply by 7, I think. Okay. So that's a little tricky to do, but I think I can manage it. Let's see. So, oh, actually, it should be a 5. I don't know why I put down 3. So that would be a 5. So that's actually not too bad, because 156 is 2 times this. So therefore I can rewrite that at 10 times 128. So therefore just make it into 3 times 128. And 3 actually divisible by 105, which actually comes out to be 35. So I think my answer is 128 over 35. So hopefully that's the same answer I got before. Let's see. As I say, moment of truth. Oh, yay, 120 over 35. So I think I got it right last time. And I hope I got it right this time also, unless I got it wrong twice. I hope that's not the case. All right, unfortunately, that's all the time I got. Just last thing I want to talk to you about is that when you're doing a triple integral, it's the same way, but unfortunately I won't be able to draw you the picture correctly because it's just hard to draw all these limits correctly in R3. But the idea is the same, is that you kind of have to rearrange the integral by rewriting the inequality. Lucky for you guys is the following. I don't really intend to make you do a triple integral or higher where you have to rewrite the integral in different order, because that will require you to be able to visually see how all the limits work out. So it's actually hard to do, but do expect that you will need to do that with double inequality, double integral, where I might ask you to rewrite the integral using a different order and see how that goes. So be mindful of that. All right, so I think that's it for today, and my video is a little too long. I apologize. We just have one more video tomorrow. The next video should be relatively short because I only have one more things I want to show you, and then that would be it. Okay, I'll talk to you guys in the next video. Okay, bye-bye.